Once we understand the singular value composition, we're ready to explain what principal component analysis is. We're going to use this example that we've used before with twin heights. Each point is it represents the height of twin 1 versus the height of twin 2, and it's represented as a matrix that has n rows and 2 columns. And the task that is related to principal component analysis is to find a projection. We're going to find a vector that defines that projection. Here we're going to call it V1. That is orthogonal, so the cross product of V1 is 1. And it maximizes the sum of squares of that projection, which can be written as shown in this last equation here. Y projected to V1, and you take the cross product of that, that gives you the sum of squares. We want to find the vector that maximizes that variability. And what we're going to see, we're going to try out different V's to sort of motivate why it is that we end up with the optimal solution. And it turns out that the optimal solution can be obtained using the singular value decomposition. So let's just try out some V's so you get an idea what's happening here. So the first V we're going to try is simply 1, 0. Right, so that's the vector. And when you project the data onto that vector, you basically get back the height of twin 1. Right, you multiply y by v. The first dimension is kept, and the second one is multiplied by 0. It goes away. And we can easily compute the sum of squares for the first dimension, and we get the number. You can see it at the top of the figure here. Now, can we do better than that? So let's just try something else. Let's try the vector 1 minus 1. Can we even use that one? Well, we can't because the cross product is not 1. So we can easily fix that by dividing by the square root 2. Now it does have that property. And we're going to try this vector v that is basically giving us the difference, but standardized to have a orthogonal transformation. So if we use this, now what we're doing is we are projecting each point to the space that is spanned by v, which is shown with the diagonal line you see there. And now we project each point, and we get the orange dots on that line. Those are the projections, so that's y multiplied by v. And we can take the sum of squares. That's easy to do. We just take the cross product, and in this case, we get a much smaller value than we did before. So this is definitely not the solution. So we can mathematically show that the solution to this problem, the v that maximizes this, is 1 divided by the square root of 2, 1 divided by the square root of 2, as shown here. This, we have seen this vector before in our videos on singular value decomposition. And this one has a very high cross product. When you map each point to the space spanned by v, you can see that it has a wide range, and it turns out that this is the solution. So this vector that we just shown is the vector that maximizes the sum of squares of yv1 transpose yv1, and it's referred to as the first principal component. That's what this v1 is. It's also called an eigenvector, and then y times v1 are the projection or the coordinates or eigenvalues. These are just mathematical terminology. But know that each row of y gets a coordinate, just one value for each row of y in the example that we've shown. Now, to get the second principal component, what we do is we take the residuals of the we subtract, you can call it an approximation, of y based just on that vector v1 as shown in this formula here. And now with those residuals, you try to find a second vector that maximizes the cross product for the residuals. And then if we had more dimensions than 2, if we had m dimensions, then we would keep going and get the third and fourth and fifth, etc., using this procedure. And that basically defines a principal component technique. That's how you find them. And again, you can find these using the singular value decomposition as shown in this code. If we apply it, you can see it right here. If you apply the singular value decomposition to y, you can see that we get these two vectors that we showed you earlier.